starting the recording. The other day, we did this standing wave activity, and you handed this stuff in, everyone in this class. And we took a look. And I'm going to show the next page because that's one where we worked one of them out. So the whole idea is that, and we're going to do some problems to follow up right now. The whole idea here is that if this spring was 3.8 meters long, and we created something with 4 antinodes, I call them loops though too, because people think of them as one loop, 2 loops, 3, 4, right? Now, that's a 2 full wavelengths, so we knew that that's how we found our wave, right? And then we timed this for 10 cycles as best we could. It was pretty fast. So. And we figured out the frequency, right? And then we used this formula, V equals F lambda. We found out the velocity, the other frequency. Now, the main formula for these things, we know that one speed formula in different situations is distance over time. But frequency wavelength, now, you don't have to memorize it, but it's not that hard if you use it. Anyway. We're going to do a couple more problems. But one thing I said in theory when we did this experiment, Jesse and me at the front, I know you've done some with me. Who was working with, oh, Josh and I did too. I know different days. Remember how we tried to stay the same distance apart so that the spring didn't change tension? In theory, the speed of the waves should have been the same every time. It didn't work out that way because we know we could hear what could be here about that. You can hear the air, right, whizzing by. That means there's friction. So things weren't staying the same. But in theory, in an ideal situation with no friction, you would not have a change in speed. Just the frequency and wavelength, right? So we're going to use that fact to do some more problems. I'm just going to hand these out. I'll pause the video. And this right now. By the way, I've started recording. Greetings and welcome to Physical Science in the Air. I'm Joel Shadell. Welcome aboard. Okay, now we're going to take a look at this here. And just keep it in mind that the formula we're going to use, speed, velocity, frequency times the wavelength, right? Obviously, there's enough space you're going to work on this paper. Only grab 2. And I'm not giving you 1,000 questions. I'm just giving you 2. So we're going to work together. And I want you to think about these as you do this, okay? Because then I will have some stuff for handling eventually. These 2 are for learning, and we're learning together. Okay? We're doing them together. A standing wave is generated in a spring that's stretched to a length of 6 meters. The wave pattern consists of 3 antinodes. The frequency used to generate the wave is 2.50 hertz. What's the speed of the wave in the spring? Okay. I need a diagram. And I suggest you, generally, if you're getting a standing wave question, or wave question generally, you need a diagram. Now, this is the spring at rest. I'm going to put a dotted line because it's like 6 meters. That's what this is. I'm going to put 6 meters down. This is like the diagram on the left, right? And then I'm going to read this carefully. The wave pattern consists of 3 antinodes. Are antinodes the spots that don't move, or are they the loops? On a test, if I write a sentence like that, I'm actually asking, part of the test is, so don't ask me, are these loops or, no, that's what I'm asking. Like, you know, it's part of the 3 loops. 1, 2, 3. I'll make my diagram now. Oh, super. There, now. And it's a standing wave, so I'm going to just draw it either up that way or this way. My drawing isn't that careful, but you guys know how this works, right? this is representing the spring up and then down at all these spots, what we saw the other day. And I know that these are three antinodes, three loops, right? Nothing. And you remember vibrating there between Josh and I, and eventually find the right rhythm to get that. Now, I want to just mention something, because on a test or another assignment, I could have given the same information, but in a different way. I said here, standing wave consists of three antinodes. I could have said 4 nodes. Because there's 1, 2, 3, 4 nodes. And it's the same problem, right? Vocabulary, nodes, antinodes, know what they mean. Know what they mean, eh? Okay. The reason why is you get this diagram. How much of a wave is that? 1 and a half. Because a wave is a full up down, right? This is 1.5 waves. Now this is easy enough, and most of you, many of you anyway, can do the arithmetic in your head. But I'm going to write this down. This is 1.5 wavelengths, right? How do I figure out what 1 wavelength is? Well, 6 is kind of easy to do. It's 3 chunks divided by 3. It's 2. That's only half of a wave, and I double it, it's 4. If you follow what I'm saying, great. If you don't, do it mathematically. And here's what we're going to say. The wavelength, from this given information, I can figure out that 6 meters for 1.5 waves, and I wrote this down wrong. I just realized. It's not 6.0 meters, it's what? 6.00. Right. That means every time I do something, it really does. Anyways, what I'm going to deal with 6.00. That's different. That means it was measured that accurately. So I'm going to. That tells me my answer. Possibly going to have 3 digits in it, 3 significant. Now, the 1.5 is actually an exact number. I can put as many zeros of measurement behind that line. We're not going to use that to make decisions about how to round. So 6 divided by 1.5. You put it in your calculator, can't do this. The wavelength is 4 meters, 4.00. We're going to say it's that accurate. That's what we were told. Now the frequency, 2.5 hertz. I'll mention something. 2.50. And I never took any marks off of this, but be very careful. Some people were putting small H Z, and I didn't take a mark off. If you see on your assignment when I hand them back tomorrow in class, a circle check mark, I mean, I'm giving you the mark, but there's a little something that you've got to improve so that when you hand something in on a test or another assignment, I'm not going to do it anymore.
I was actually wondering, because I just wrote another lowercase h. I just wrote it because it's easier
You
to
were one
write.
of the people that, I can't remember who they all were. Between the 2 classes, I just marked 60.
I was like, should I put it?
And it was 1 in the morning when I finished, so I don't know who. You are. Okay. So, and just for example, too, like meters, use a small m. Later on in this course, we're going to have a big M for something else. Don't worry about what it means right now. Moles per liter, but what's a mole? Who knows? You'll find out. It means something different than small. So capitals and small case letters are on purpose. I use them on purpose. I model my units are always shown on the answers. If I screw up, you guys call me out. So the formula is V equals M lambda, and apparently we're supposed to find the speed of the wave in the spring. I have to read the question. This is pretty easy now. I have to do a little figuring out the wavelength. 2.50. Use a calculator. Oh, I just talked about the importance of units. I didn't put them in there. Hertz, which means per second. So if you want to put second minus 1, that's fine. second one, power. Okay, 2.5 times 4.
Okay.
There you go. And guess what?
No, 10.00, right?
10.
Or 10.0.
Why 10.0? You're right.
The 6 is just 6
Three
points.
digits in, 3 digits. We used 3 digits that were measured there, 3 digits that were important enough to list there. Never count fractions. So 3 digits out. That means not just 10. If I say 10, I'm like, it could be 9.5, could be 10.4. You know what I mean?
Definitely.
This is 10.0. That's important. I think you guys know. Now, another question. I'm going to make a dividing line now. Maybe something fun. I like flowers. Flowers it is. You have your flower
Wait, our
pen.
answers are on the page.
Yes, they are, top right corner. I circled that. Oh, yeah. So, if you're just going, this is for practice and stuff like this, not for marks. I want you to have the answer. Okay. Number 4. When a string is stretched to a length of 8 meters, the speed of the waves in the string is 5. I'm going to actually write beside this one. That's my speed velocity. The simplest standing wave pattern for this string is that of a single antinote, one loop. Between 2 notes, they give both pieces of information. They didn't have to. At the opposite ends of the string. I'm going to just draw this before we start. 5 meters per second, but it's a length of 8. Now, I know that a single loop, that's a single antinote. It goes up, and then it goes down. And it goes up. This is like skipping rope, right? The easiest one to do is the slowest. Right away, then, what does this tell me before I even start the call? How much of a wave is that? Half of a wave. Now, you can do this in your head because 8 is an easy number to work with. If you know that 8 is the length of half of the wave, the whole wave is, double it, 16. If you're of the mind though that like, yeah, I wouldn't say it, it makes sense, but I need a calculation. You go like 8.00. You don't have to show this work. You can just write down 16. But the way I get it is, so this is half of a wave, right? I can make this as accurate as I want. I can make it 0.5, 0, 0, 0, 0, 0. I'm not going to go forever. I'm not using this to make decisions about significant data. That's exactly how it works. Just like the other one was 1.5 of it. If you enter in 8 divided by 0.5, it comes out to be 60. But there's no reason why you have to do it that way. You can just do it in your head. No, right? Use logic, whichever way you want. And now I'm going to read it. What's the frequency that produces this standing wave? Well, this is pretty easy. I got V. I now have lambda, the wave length. Equals that lambda. You guys told me you like plugging in the numbers and then solving, so I'm going to go with this. We're looking for F, so I'm going to put in V equals 5.00. I just slid down. Yeah. 1,000 meters in seconds, not in centimeters, so everything matches. The frequency is what we're looking for, times 60. Algebraically, we're going to get the F alone by, I just divide by 60. When I make a circle on this, you know how to I make you disappear. I don't actually have to show that word. Okay, you know what I'm trying to do. I'm trying to go 16 divided on both sides. So F equals, when you divide 5 by 16, it's at the top of the page too, but work the calculator. It's actually 0.3125, I'm pretty sure. Why did we go 313 though? 3.125? Yes, that's not, I'm gonna put that in green and then erase it. We only need 3 digits. So then I have to use proper rounding. You're gonna get used to this. I'll still give you full marks at this point. For 3135. Or 3125. Start easy, make your life easy so it's not a big. 3 digits in, 3 digits out. Don't keep a full decimal expansion. Don't just put 0.3. Keep enough digits. Just get used to this. Then we'll start a jerk about it. The feet. This is something I mentioned earlier. What is the next higher frequency for which a scanning wave exists in the spring? Now, I mentioned this. I said with Josh and I, we didn't move closer together, and we did our best to keep our hands about the same spot. What did I say about the speed in theory without friction? Whether I've got 3 antinodes, 4 antinodes, 5 antinodes, how should the speed be in all those situations if I haven't stretched the spring? Should be the same. So I'm going to put that down in the fact, but we should be able to use that speed. What's the next higher frequency? So speed is the same. I'm going to put that in words. Speed, I started hammering. Because it's the same spring set. Okay? So V would be 5.00. We're ignoring friction. It would change. Good luck finding a frictionless system. If you're not changing the length of a rope or a spring, yes. Good. The next higher frequency in which the scanning wave exists in the spring. So we've got the same length, 8 meters. Same spring. What is the next set of, what's the diagram going to look like? Right. So instead of this, we'll have this. I'll draw it again. Well, 1 loop, 1 antinode. What's the next logical spot? 2.
Oh,
then 3, and then 4. Yeah. So separating it. So this is the 8 meters. We know that it's going to go up, down, and then a second later, down, up. This is our next one. Can you guys just see this? There's no calculation required. How much of a wave is this? It's 1 full wave. In this case, because it's got 3 nodes to it, this is wave length. I'm fine if you're doing this problem on your own. You didn't list that explicitly because it's pretty logical. There's nothing quite to figure out. So, but it's not really this B problem is remembering that the speed, if I didn't change the length, the speed is then I'm going to solve it, right? That's going to be 5 divided by 8. So when you do 5 divided by 8, this time instead of hertz, I'm just going to spice it up a little bit. Same thing, right? I don't care which one. Put hertz down if you like. Numerically, what actually happened to the frequency? It went up by a factor of 2, right? Like it doubled. And Josh and I, when we were trying to generate these the other day, so, I get used to just this standing wave and I'd be rocking my hand back and forth with Josh. Then to do the next one, you got to double your hand speed or whatever, right? And it's like, your hand gets tired after a while when you're trying to do five, you couldn't keep it, right? So then you're like, I'm doing this. Five like loops. Oh, I put seconds to the negative one, that means per second, the exponent of -1 means downtown on the bottom. It means the same thing as hertz. I want to get you used to seeing hertz or seconds. Let's go 10 foot in hertz. But that just means per second. So I don't care if you use 8 zip. Go ahead. Yes.
We use 8 again for the waveline.
Yeah.
Is that could be divided 8 by 1 into 15?
Yeah. If you really want to think of it as a calculation, okay. That is, we're going to have some practice.